Hi everyone. So welcome to this video. So I want to continue answering science paper 1. So this is a paper that was written last year on 7th November. So I've already answered question 1 to 5 in this paper. So I just want to continue from question 6. Then we proceed like that. Okay. So if you haven't watched my first video where I explained the first 5 questions, then you can just go back to our videos, try to watch it, then you learn something there. Okay, otherwise, let's just get started. Okay. So this is what we've already answered. If you want, you can be taking screenshots. You can take a screenshot here and see what we discussed. This is what we did in question 2, question 3 there. You can be pausing and take screenshots. Question 4. This was question 5. Okay, so today I want to start from question 6. Okay, so question 6 says the diagram shows a vacuum flask labeled with 5 features, each one designed to reduce heat transfer. So this is a vacuum flask. Some other students would call it a thermos. A thermos flask. You can also call it a thermos flask. So this is equal to vacuum. Okay, yeah. Okay, so what does this flask do? What is a thermos flask? So this is a special flask that is able to keep hot liquids hot and cold liquids cold for a longer period of time. So it maintains the temperature of a liquid. Okay, so you're going to have a liquid in there, then you can maintain the temperature of the liquid for a longer period of time. So it is designed in a way that enables it to reduce heat loss. It can also reduce heat gain so that whatever is there is kept at the same temperature for a longer period of time. So here the question says, which labeled feature of the vacuum flask reduces heat transfer by both conduction and convection? Okay, so both conduction and convection. So first of all, you should also know that there are three modes of heat transfer, okay? So we have 3 modes by which heat can be transferred. Number 1, we call it radiation. Radiation. Number 2 is something called conduction. Number 3, we have something called convection. Okay, so these are the 3 modes of heat transfer: radiation, conduction, convection. Now, what you need to know is that radiation is the transfer of heat through an empty space. It can transfer through it's a transfer of heat through waves, through infrared. Okay, yeah. So heat can be transferred without material, without particles. Then we're talking about radiation. But where you need particles now, we have conduction and convection. Okay, so conduction is the transfer of heat through solids. It's the transfer of heat through what? Solids by vibration of particles. Okay, so this one involves the vibration of what? Particles. Then convection is the transfer of heat through fluids, meaning through gases or liquids, mainly by the movement of the heated particles. So the particles are heated, then they begin to move. Then conduction only by vibration of what? Particles. Then radiation can transfer through what? Infrared. Okay, it's an through electromagnetic waves. So heat does not need material here. Yeah. So the question says, which one prevents heat loss by conduction? I mean, conduction and convection. Okay. So what we know is that, okay, so we have a liquid there, okay? You have a liquid there. So what is the purpose of the silvered? So you have these double silvered walls, okay? Double silvered walls. Most of the times they are silvered, okay? Yeah. So what's the purpose of the double silvered walls? So we know that heat can move. So heat can move by radiation in an empty space. This vacuum here, heat can move by radiation. But once heat moves by radiation, we have the silvered surfaces here. Have you seen these silvered surfaces? They are able to reflect heat back so that it is not lost. So the purpose of the silvered inner surfaces is to prevent heat loss by radiation. Okay, to prevent heat loss by what? Radiation. Then this one, this part here, sometimes they can ask you, this part is a cork stopper, not labeled there, but we can talk about it for future questions. It's a cork stopper. Okay. Yeah, so this is mainly made of rubber or plastic. So usually this one is a bad conductor. It's a poor conductor of heat. So it prevents heat loss by conduction. It can also prevent heat loss by radiation because heat can be moving upwards like that, okay? Convection, okay? By convection. It can also prevent heat loss by convection. Heat can be moving upwards, so it will prevent the heat loss upwards like that. Yeah. So it's a cork stopper. Then this vacuum prevents heat loss by conduction and convection. This vacuum has no what? So this vacuum, there are no particles here. No particles. Okay? And if there are no particles, it means that heat cannot be transferred either by conduction or convection. Remember, I said conduction needs vibration of particles. Convection also needs movement of heated particles. So because in a vacuum you don't have particles, then heat cannot be transferred by both conduction and convection. Okay. Yeah, glass is also a bad conductor of heat. So if you have glass here, this glass can also prevent heat loss by what? Conduction, because it's a bad conductor of heat. Yeah, but the silvered surfaces, because it's silvered here, this is silvered, it can prevent heat loss by what? Radiation. Once heat moves through a space here, it will also be reflected backwards. And heat coming from outside there, it can also be reflected away. Okay, so the best answer here was D, the vacuum. So D. And you should understand why D is the best answer here. Okay, we go to question 6. Question 6 says a given mass of air occupies 24 cubic centimeters at normal atmospheric pressure. So that is the volume. What volume will the air occupy if the pressure is increased to 4 times the original value without changing the temperature? Okay, so we have our initial volume here. Let me call it V1. This is the initial volume of what? Air here. So you have air. So you have a container that has air in it, okay? So we have air molecules there. And these air molecules initially have a volume V1, which is 24 cubic centimeters. The question is, what volume will the air occupy? What will be the new volume if the pressure is increased? We increase the pressure. Imagine maybe you are applying, you're squeezing there so that pressure increases there inside. Imagine you're squeezing. What do you think will happen to the volume at constant temperature? If you are squeezing, it means this container will shrink. So in other words, the volume that the air will occupy there will reduce. Okay? So we don't expect the answer to increase. So these are not answers, just from understanding what's happening there. Okay? Yeah. But what I also want you to understand is that because they've mentioned what? Constant what? Temperature. You're not changing the temperature. This question is testing you on something called Boyle's law. Okay? It's testing you on something called what? Boyle's law. Yeah, Boyle's law. Now, what is Boyle's law? So, according to Boyle's law states that at constant temperature, if the temperature is constant, the volume of a fixed mass of a gas is inversely proportional to the what? Is inversely proportional to the pressure. Okay? So, the volume and the pressure are inversely related to each other. So I can write this as P is equal to some constant K divided by volume. Okay? Or you can just write this, you can cross multiply here and say P times V is equal to K. So you usually see this as PV is equal to K. That is Boyle's law. Okay? So PV is equal to what? To K. Okay, let me bring it here. So that is Boyle's law. Now, what does it mean? It means that if you keep the temperature constant, it doesn't matter which value of pressure and the value of volume you get. If you multiply them, you always get a constant value. Okay? Meaning, if I have pressure 1 times volume 1, I will still get the same value as pressure 2 and volume 2 multiplied together. So this is the common form. You see Boyle's law written like this. So we can now use this part of Boyle's law now to figure out what the new volume will be. Okay? Because what they've asked us here is what is the new volume if we increase the pressure to 4 times the original. So let's use this Boyle's law now. Let's use Boyle's law. So pressure 1, let me just, because they didn't give us the exact value for pressure 1, so let me just say pressure 1 is P. Okay, so I'll just say P is pressure 1 multiplied by volume 1, which is 24 cubic centimeters, of course. Yeah, so this is equal to pressure 2. They've said you are increasing the pressure to 4 times the original. So our new pressure is 4 times the original pressure. They multiplied by volume 2. So volume 2 is what we are trying to find now. So let me just call it V2 like that. Okay, so you can see here now that, you can actually now cancel. Okay, so you can now divide, you want to find V2, you can divide both sides by 4P. You also divide there by 4P. So this and that will cancel, remain with V2. P and P will cancel. 4 there, 1. 4 there is what? 6. Okay, so you can see V2 is equal to what? To 6. Yeah, so this gives us now our new volume. V2 is equal to what? 6 cubic centimeters. Like that. Okay, so this is the answer. And you can see that just like we predicted, the answer has to be less than 24. Yeah, so the best answer here was what? A. Okay, let's move on. So what is the wavelength of a radio wave whose frequency is 3 million megahertz? 3 megahertz or 3 million hertz if you want. Yeah, so what is the wavelength of a radio wave whose frequency is this one? And it travels with a velocity of what? 3 by 10 to the power 8 meters per second. So they're asking you now, what is the wavelength? If we've given you the frequency, so they've given us the frequency, small letter f. They've also given us the what? The speed here, v. Then what is the wavelength? We use the symbol, this one. Want to find the wavelength. So this is a symbol that you see for wavelength, lambda. Okay. So I want you to introduce you people to something called the wave equation, okay? The wave equation. So we're going to use the wave equation. Now, what is this wave equation? So this is how the wave equation looks. So the wave equation now is an equation that tries to relate the wavelength. It tries to relate the speed of the wave with the wavelength and the frequency, okay? So the speed of the wave v is equal to the frequency multiplied by the wavelength. So multiplied by the wavelength here. Like that. Okay. So now what we have here is, they've already given us the speed is 3 by 10 to the power 8. We also know the frequency, but the frequency here is not in SI units. The SI units should be in hertz, like that. So we need to remove this capital letter M. This capital letter M is read as mega. Mega. Okay, capital letter M. And mega means a million. It means 10 to the power 6. So it means 10 to the power what? 6, like that. So here, instead of saying 3 million hertz, someone can now say, so this 3 megahertz is the same as saying 3. Oh, this is 3 here, not 30. So it's the same as saying 3 times what? 10 to the power what? 6. So we've removed the what? Yeah, we've removed the mega there. Okay, now that we've converted the frequency to the SI units, which are the hertz, let's now use this equation to find the what? The wavelength. So it means that our wavelength here, if we make wavelength the subject here, you will see that wavelength is equal to the velocity divided by the frequency, right? Okay, so it means that our wavelength is equal to, the velocity is 3 times 10 to the power 8, right? This one here. Then the frequency is 3 by 10 to the power what? 6. So this and that will cancel. 10 to the power 6 will cancel. There we're going to have 10 to the power 2. Or if you want, you can use your calculator here. And 10 to the power 2 is simply 100. Okay. So meters. Yeah. So meaning our wavelength here was what? 100 meters. So the answer here is B. Okay. Let's go to question A9. The diagram shows a waveform. So this is a waveform. What is the period of the wave? So just like we looked at period of the pendulum, we also have period of the wave. We can also now define the period here in relation to the wave. So period of the wave is also the time taken to make one complete vibration. By one complete vibration, I mean one complete wave. This is how you count one complete wave. From there, you move like that up to there. Okay? You should have one, this is a crest and a trough. So meaning period should contain one crest and one trough. So like that. Okay? Yeah. So in other words, the time it will take for the wave to repeat itself, the time it will take for the wave to restart the new cycle is the period to make one complete wave. So how many waves do we have here? This is half. From there to there is half vibration. There, complete vibration. So 1.5. So we just have 1.5 vibrations here. In other words, we just have 1.5 waves. Now we want the time it takes to make one complete. So you can see the time we're getting it from the x-axis here. So one complete vibration is like that. So the time it takes is what? 4 seconds. Yeah. So the period here is 4 seconds. Very easy. Okay, so sometimes they'll ask you what is the amplitude. So this distance is the amplitude. This one. Amplitude is the maximum displacement a particle moves from its rest position. So from there to there, if we had a value there, that value represents the amplitude. If this was distance here, not time, if they had put distance, okay, distance in meters, like that, the distance it will take to make one complete vibration like this, that is the wavelength. Okay? Yeah, we'll share other videos now where I'll explain more about all this. Okay, let's go to question 10, and this is the last question for this problem. For this video. So question 10 says, a person fires a gun, and here's the what? Here's the echo from a cliff after 4 seconds. Okay, so we have echo here. How far is the cliff from the person, of course? If the speed of sound in air is 340 meters per second. Okay, so we have this person. So this person does what? They fire a gun. Okay, so they have a gun there. Then there's a cliff here. So when they fire a gun, so sound moves like that. Then they hear the echo. It means that this sound wave that was sent has been reflected off the barrier. It's gone back to the person. That's what we mean by echo. Echo is the sound wave that is reflected, okay, bounces off a barrier, then goes back to the person. Okay, yeah. So we're going to hear what? An echo. So they're saying they hear this echo 4 seconds later. So they fire a gun in the air, then sound is sent, then it reflects like that. So you can see that the distance between the person and the cliff is D. We're going to call this distance D. So once this person fires the gun, sound is sent like that. It covers the distance D. Then it goes back again to the person. So you can see that it covers the same distance twice. Okay? So what we know usually is that speed is equal to, so speed is equal to what? Distance over time. We know that. Now, this time around, We are going to do some changes now to this formula because we send this sound wave, then it hits the cliff, then comes back. It covers this value D twice. So instead of saying D, I can just say 2D because it covers the same distance twice. Now, our goal is to find the distance. What is the distance between the person and the cliff? What is the value of D? Yeah. So what do we do here? So we just use this formula and find value. So the speed has already been given to us. It's this one, 340. So we say 340 is equal to 2D divided by what? The time. We know the time it takes is what? 4 seconds. So divided by 4. So you can see here that this is the same as you have 340 here. 340 equal to 2D divided by 4. So you can see 2 there 1, 2 there 2. Then this is the same as over 1. So you're going to cross multiply. 2 times 340, you get your D as 680 meters. Okay, so the best answer here was what? B. And this is the end for this video. So please watch out for the next video where I'll also explain now about question 11 up to question 15, then 15 to 20, then we're done with section A, just like that. Bye-bye.